Okay, so we will do the final topic of the evening. So this is one of my favorite topics. It's a lot of fun. So we're going to be doing integration via trigonometric substitution. Integration via trigonometric substitution. Okay, so I will shorten this by just saying quote unquote trig sub, right? Because it's a mouthful otherwise. So I will just say trig sub in quotes, and that's usually what people or teachers call it. All right. Okay, so what do we use trig sub for? So which is the general theme of the first half of Calculus 2, is that we want to enlarge our toolbox of how to integrate functions. All right, so now we can integrate powers of cosine and sine, tangent and secant. Well, now we want to enlarge our class of functions that we can integrate. So it's used to integrate. It's used to integrate. Actually, let me just change that. Hold on. It's used to evaluate. It's used to evaluate. Sorry. It's used to evaluate integrals whose integrand contains the following expressions. So used to evaluate integrals whose integrand contains square root alpha squared minus x squared, comma, square root alpha squared plus x squared, comma, or square root x squared minus alpha squared. Okay, and here, alpha...
a constant here, right?
Correct, yes. Alpha is just going to be a positive constant. Okay, so alpha is a Greek letter. It's denoted as such, and in our case, it will represent some positive constant. Okay, so each of these three expressions, these square root expressions, they will each be one case. So we're going to have three cases. Right. So that's the deal. So let's look at case one. Case one. So case one, as I just said, it will be integrals involving that first expression there, which is square root of alpha squared minus x squared. Right, and again, alpha is a positive number.
Does it have to be an integer, or it doesn't matter?
It does not need to be, but we will work exclusively in the case when it is.
Thanks.
But it does not need to be, yeah. Okay, so what is the method? So here's kind of like the general idea. The method is to make the following substitution. Is to make the substitution. What is the substitution? It is x equals alpha times sine theta. Okay. So we do a substitution. It's like u sub, but now we're doing trig sub. We're going to let x be alpha sine theta. And then, so this is just a general idea. It's not a strategy. And then evaluate the integral as a trigonometric integral. Trigonometric integral, because we know how to do those now, as a trigonometric integral. Then substitute back in for x. And substitute back 4x at the end. All right, so that is the general kind of intuition of what we're going to be doing. So first of all, where in the world did I get that substitution x equals alpha sine theta? Why am I doing that? All right, so here's kind of some intuition as to why that works. To see why x equals alpha sine theta works, look at the following. So look at this. So remember our expression. It was the square root of alpha squared minus x squared. Okay, so I'm just going to take a moment to pause this. I want to make sure everyone is up to where I'm at. So
the circle function, right?
What was that?
It's essentially the circle function.
Sine theta?
I mean, no, the square root of alpha. I mean, it's the so alpha would be the radius, and to get the y coordinate. That's why I'm thinking you can substitute in.
Yeah, I never even had thought about it like that. You're correct. This kind of traces out the upper part of a circle.
Yeah, and r sine theta is equal to x with like polar coordinate.
Yeah, nice. We're going to do polar coordinates at the end. Very cool. Okay, so to see why this works, look at this expression. We can factor an alpha squared out. So this becomes 1 minus x squared over alpha squared. Okay, and then I can bring the alpha squared out as just an alpha. All right, I hope that's okay. And then this looks like 1 minus x squared over alpha squared. Okay, so here's the deal. The radicand, which is that expression, it resembles the trig identity. 1 minus sine squared theta. Okay, so it looks similar. We have 1 minus something squared, and it kind of looks like a 1 minus sine squared theta. So if we let x squared over alpha squared be sine squared theta, this implies that x will be alpha sine theta, which was our stated substitution. So that's a little bit of intuition as to why this kind of makes sense. All right, so this is nothing you're going to be tested on. I'm just trying to motivate why we're doing these things. Why are we letting x be alpha sine theta? Well, it kind of just things kind of work out. All right, so that's that. And let me just put down a quick note before we do an example. Quick note. Okay. The trig identity sine of 2 theta equals 2 sine theta cos theta will come in handy. Will be useful. All right, so let's just keep that in the back of our heads. We're going to use it at some point. So. Okay, all right, so let's actually get down to an example here. Okay, so the example is this. It's going to be the integral of the square root of 9 minus x squared dx. Okay, so let's just recall what case we're under. We're underneath the case where we're looking at integrals that involve alpha squared minus x squared. So if alpha squared is 9 in our case, that means that alpha will be 3. All right, so we're working now in the alpha equals 3 definitive case. All right, so I hope everyone's okay with why alpha is 3. Okay, so remember we were told that we make the substitution x equals alpha sine theta, so we do the substitution. X equals 3 sine theta, okay? So that is that, and whenever you do a substitution, you also have to find dx. So that means that dx will be 3 cosine of theta d theta. Okay? Because that's the derivative of sine. Okay, very good. Now, we're going to take this integral in terms of theta, all right, with our new substitution. So integral, square root, 9. Now, we have 9 minus x squared. X is 3 sine theta, so that means that x squared will be 9 sine squared theta. All right, so this is x squared. And we need our dx. That's going to be 3 cosine theta d theta. Okay, so this is our integral, this is our integral. But now in terms of theta. Okay? Hope everyone's okay with of what's going on here. This dx is 3 cosine theta d theta. That's why I put that right there. Okay. So this is dx. Very cool. So what's going to happen now is that we can factor a 9 out from that square root. So 9 times 1 minus sine squared theta. I'm going to bring the 3 out front, cosine theta d theta. Okay? So I just factored a 9 out from that expression that's underneath the square, that's in the square root. Okay, so let's be careful now. I can pull this 9 out of the square root, but it doesn't come out as a 9. It will come out as a 3. All right, I hope everyone's okay with that. So that will become 3 times 3. So this square root of 9 came out as a 3. All right. All right, so I hope everyone's okay with that property of square roots. Okay, hope everyone is still with me. Now, the 3 times 3 out front will just be a 9. And I can rewrite this 1 minus sine squared theta as the square root of cosine squared theta. All right. And that's very nice. Hope everyone's with me so far. Now what's really nice about this is that we have the square root of a square. So this just becomes cosine theta. That's what this whole thing comes down to. And then the cosine theta d theta also comes down. Cosine theta d theta. Okay. And then we now have cosine squared theta d theta. Okay. Hope everyone is okay. I'll give it a minute. I know there's a lot of algebra going on. Okay, so let's recall from last class. How do we integrate cosine squared? What's the deal? What we do is we rewrite this using the double angle formula. All right. So we rewrite this as 1/2 1 plus cosine of 2 theta d theta. Okay, and this is by identity. Okay. Okay. Now I will finally take the integral, all right, after all of these algebraic steps. So this will become 9 times theta over 2 plus 1/4 sine of 2 theta. Okay, and this is by taking the integral. Okay. So I hope that's cool with everyone. The integral of cosine 2 theta, a 1/2 pops out by u sub, and that 1/2 combines with this 1/2 to create a 1/4. That's why there's a 1/4 here. All right, good. Let me just distribute the 9 in. 9 theta over 2 plus 9/4 sine of 2 theta. And let's now use that identity for sine of 2 theta that I wrote down before. 9/2 sine theta cosine theta. Okay, and this is by...
Are we going to want to substitute back into x?
That is the next step, exactly. So unfortunately, we're not done by trig identity for sine of 2 theta. So that was this last step here. It was by the trig identity for sine of 2 theta. All right, so let's all take a breath. I know there's a lot of steps going on. If anything is terribly unclear, please let me know before I move on.
I just want to double check that 1/2 in front of your integral.
Right here.
4 steps up. If you put that in front of if you made it 9/2 and then the integral of whatever afterwards, would that be fine, or did you need to?
That would have been 100% fine.
Okay.
Would have gotten the same thing for sure. Okay, so the most common mistake that I see now is that students think that we're done with the question. We're not. So, warning, we are not finished. Okay? So I want everyone to just make note of that. We're not finished. We need to substitute back in for x. We need to substitute back in for x. All right? So if you stopped here, well, you wouldn't get 0 credit, but you would not get full credit. Okay? All right, so how do we do this? Okay, we now need the above expression. So let me copy it down. Okay, we now need the above expression, which is this, in terms of x. Okay. So that's how we finish the problem. We rewrite this guy in terms of x. And then we're done. Okay, so how do we do this? Well, what the strategy is it's good to draw a right triangle. So it is useful to draw a right triangle using the fact that x is equal to 3 sine theta. So we draw a right triangle using the information from our initial substitution. So that's kind of cool. So if x is equal to 3 sine theta, that means that x over 3 is equal to sine theta. So this is what we're going to use. So now we're in kind of that same position when we were taking derivatives of the inverse trig functions. Okay, so from star, we can draw so what do we get from star? Well, let's get our right triangle, make this theta. Okay, so remember, sine is opposite over hypotenuse, so I know that opposite will be x, and hypotenuse is 3. So this is directly from star, all right? So remember, this is opposite over hypotenuse. Very good, and then by Pythagorean theorem, we can quickly get that this missing side is 9 minus x squared. So that's by Pythagorean. Okay. Okay, very good. So we see that cosine theta can be easily read from this triangle. It's going to be adjacent over hypotenuse, and that will just be the square root of 9 minus x squared over 3. All right, good. So let's just recall what we need. I'm going to copy it down again. All right, so we need theta, sine theta, and cosine theta. That's all the pieces we need to rewrite in terms of x. All right, we already have sine theta and cosine theta. We just need theta. Well, that's not too bad to do. Recall that x over 3 is equal to sine of theta. And now you can just apply inverse sine to both sides. And we get that theta will be arc sine of x over 3. All right, so we now have everything we need in terms of x. All right. Thus, 9 theta over 2 plus 9 over 2 sine theta cosine theta equals 9 over 2 arc sine of x over 3 plus 9 over 2. Okay, and what was our expression for sine? It was x over 3. And our expression for cosine was the square root of 9 minus x squared over 3. All right, so this is sine theta, and this is cosine theta. All right, so that's why we drew the triangle, was so we could read off these values. Okay, and final step, just to clean up that right term, arc sine of x over 3, we get plus x square root of 9 minus x squared over 2. Okay.
Would you be putting parentheses around something?
No, I think that's correct because that's this term right here.
Where did the 9 go?
The 9 canceled out with this 3 times 3.
That would do it.
Yep. And then we have a plus C. Whew. That's a long one. I hope everyone is not too upset by this question. I know it's pretty lengthy. So I'll just give everyone a second. Okay, so any questions on steps? I think things will become way clearer once we do some examples, and homework too will have examples. All right, so let's do another one. Let's do another one. Okay. So we're still under case 1. All right, here's the example. Integral 1 over square root of 1 minus x squared, that quantity cubed, dx. So we are in case 1 because we have a number minus x squared. Okay, so we are in the case where alpha is 1. All right, so let's just kind of keep that in the back of our heads. We're in case 1 when alpha is 1. Now, it may be helpful to rewrite the denominator as 1 minus x squared to the 3 over 2 power. Okay. So I hope everyone is okay with that part. We're just rewriting the square root as a 1/2 power. Okay. So the substitution is x is equal to alpha sine theta. Well, alpha is 1, so x is just going to be sine theta. And that will then imply that dx is cosine of theta d theta. So do not forget the dx. Very important. So just warning, don't forget the differential dx. Okay. Very good. So now let's bring this whole integral in terms of theta. All right. So what will that give us? This is now equal to the integral. Now in the numerator, we have just a dx. So I will replace that with cosine of theta d theta. And this will now become 1 minus sine squared theta, that thing raised to the 3 over 2. All right. So this is just by our substitution. All right. So I hope that's clear. Oops. Cool. So the 1 minus sine squared theta, this will become a cosine squared theta. So that's the deal. So the denominator will just be cosine squared theta, that thing raised to the 3 over 2. Okay. So this is by trig identity. Okay, I hope that's cool. I just rewrote this 1 minus sine squared as cosine squared. Awesome, and that's really good because then the bottom just simplifies to cosine cubed. Okay. Very nice. This comes out to 1 over cosine squared, which is just secant squared. And this is an integral that we know. This is tangent. So not that bad. So I hope everyone is okay. So that's why I think that trig sub is so amazing. We had such a complicated integral, and it just came down to be tangent. So that's pretty cool, I think. Okay, we're not done yet because we need to write this thing in terms of x. So I'll do that if there's no questions. All right. So remember, from our initial substitution, that is what we use to draw our triangle. So from x equals sine theta, we can draw the following. All right, so we've got our right triangle, theta. Okay, so sine of theta is opposite over hypotenuse, so this will be x over there and 1 at the hypotenuse. And then by Pythagorean, this will be 1 minus x squared. Okay. Hope that's cool. So let's just recall the information that we need. We need tangent theta. We need to rewrite tangent theta in terms of x. Well, that's easily readable from this triangle. So now it's clear. Now it's clear that tan theta, which we recall is opposite over adjacent, will just be x over the square root of 1 minus x squared. All right. So this one came out to be a lot nicer. This is just x over the square root of 1 minus x squared. That's just by trig. And there we go. So our final answer is just that. Our final answer is x over square root 1 minus x squared. We're finished, so we put the plus c. Okay. Any questions? I hope everyone is still on board with me. This one was a little simpler than the first one. Maybe I should have started out with this one. Okay. So if everyone is okay, I will move on to case number 2.
Can I ask a question real quick?
Sure.
Okay, so basically the whole trig thing where we're doing the right triangle at the end is because we are using all the different trig identities, which uses theta. So when we're doing those trig identities, we're substituting theta in for x. So then that's when we have to do that.
Yes. So, right. So the point is that our integral was given to us in terms of x. Thus, our answer needs to be also in terms of x. We can't answer, we're not done if our answer is in terms of theta. So once you finish taking the integral in theta, that's when you draw the right triangle.
Right. Yeah, I just wanted to clarify because obviously you're not always substituting theta in when you're doing all this stuff. I was just clarifying when we would need to do the right triangle drawing and going back and substituting.
Oh, right. Yeah. So you would just do this triangle business when you do a trig substitution and after you have finished taking the integral. So let's just go up. We finished taking the integral from here to here. And then,
right, so every other problem we would do, that would be our final answer. Right there, plus c would be tangent theta plus t.
Right. Yes.
Okay.
But this is a more involved case. But yeah. Okay. Case 2. So we're going to do case 2, one example of it. Case 3, one example of it, and then we'll be finished. So case 2. So these are integrals involving. We're looking at now alpha squared plus x squared. All right, so here, what's the substitution here? Here, we make the substitution. We look at x equals alpha tangent theta. Okay. And why do we do that? Well, I'm not going to write out the whole thing like I did before, but essentially, if you factor out an alpha squared from this radical, and then it comes out as an alpha, you have 1 plus something squared, and 1 plus something squared resembles the trig identity 1 plus tangent squared. All right, so that's kind of the intuition as to why we do this substitution. Okay. All right, so example. Integral dx over square root of 1 plus x squared. Okay, so what's alpha in this case? We have something squared plus x squared. Alpha here is 1. Okay. Alpha's 1. Oops. Right. So since alpha is 1, we make our substitution be x is equal to 1 times tangent theta. So x is equal to tangent theta. Don't forget the dx. That implies that dx will be secant squared theta d theta, because that's the derivative of tangent. All right. So now we can bring our integral in terms of theta. So the numerator is dx. So I will now write secant squared theta d theta, because that's what dx is. Very good. And in the denominator, we have a 1 plus tangent squared theta. Hope everyone's okay. I just rewrote our integral into theta. Good. So now we notice that this radical, the radicand is actually secant squared theta by the identity. 1 plus tangent squared is equal to secant squared. Awesome. So integral secant squared theta d theta. Now, in the bottom, we have the square root of secant squared, which is just secant, because the square and the square root cancel out. Hope that's okay. So I just used the fact here that the square root of secant squared theta is equal to secant theta. That's all I did there. Beautiful. And this will reduce down to the integral of secant theta d theta, just by canceling out some powers. And luckily, earlier in class, we derived this integral. So this came out to natural log of secant theta plus tan theta. And this is just by earlier in lecture. Okay. So this was not that bad. So we're not done yet. So let me just put another warning. Warning. Need to substitute back in for x. All right. So as I said before, I've had students in the past stop here. And that's not good. Because the problem is not finished. Need to substitute back in for x. All right, so what do we need? First of all, we need secant theta and tan theta in terms of x, right? In terms of x. So let's figure those out. All right, so from our initial substitution, x equals tan theta, we draw. So you're always going to use your initial substitution as the data to draw your triangle from. Okay, so all right, so here's our right triangle. Very good. So tangent is opposite over adjacent, so I'm going to put an x here, a 1 here, and then by Pythagoras, the hypotenuse will be 1 plus x squared. All right, so I got that hypotenuse there by the Pythagorean theorem. That's by Pythagorean. Okay. Very good. So let's just recall what we need. Secant theta and tan theta. Those are easily readable from this triangle. Very easy. So secant theta, first of all. This will be hypotenuse over adjacent, the reciprocal of cosine. And that comes out to the square root of 1 plus x squared. Over 1. If you want these. All right, I hope that's okay. And what else do we need? Oh, well, we need tangent theta, but we already have that. Tangent theta was just x. All right, final answer. Final answer. So recall, we had ln of secant theta plus tangent theta. This will equal natural log. Secant theta we figured out to be the square root of 1 plus x squared. And tangent theta was just x. All right, so that went there, and that went there. Any questions? Okay, so if everyone's okay, I'm just going to move on to the final case, and then we will be done for the evening, okay? All right. Okay, case 3, third and final case. So this is going to be integrals involving the square root of x squared minus alpha squared. Okay. let's see. And what is the correct substitution for here? We use the substitution. X is equal to alpha secant theta. And the reason for doing that is after you algebraically change this radical, it will resemble secant squared theta minus 1. Right? So that's kind of the intuition. Very good. So let's just jump into an example. All right. So integral dx over square root of x squared minus 4. Excuse me. So does anyone, would anyone like to tell me what alpha is in this case?
So 2.
2. Yes, exactly. Alpha's 2 here. Perfect. So alpha's 2. Awesome. And we're told to let x be alpha secant theta, so we're going to let it be 2 secant theta. Okay. Very good. So don't forget the dx. That's another common mistake. So the derivative of secant is secant times tangent. Okay. Secant times tangent d theta. Great. So now let's bring this integral into theta. So the numerator is just dx. Okay, so the numerator, I'm just going to put this guy. So 2 secant theta tan theta d theta. And the denominator will just turn into 4 times secant squared theta minus 4. Okay, I hope that's clear. I just wrote this integral into theta. All right. So I'm going to factor the radical. So 2 secant theta tan theta d theta, copy down the numerator. I'm going to rewrite that square root as 4 times secant squared theta minus 1. And I hope everyone agrees with me that out will come a 2 from that square root. Okay. So we get 2 secant theta tan theta d theta, and a 2 will come out of that square root. And let's also note that secant squared minus 1 is tangent squared, and it's underneath a square root, thus you will just get tangent. Okay, so I kind of skipped a few steps in there, but I hope that's okay. Okay, so now we get some cancellations. The 2's cancel and the tangents cancel, just leaving us with the integral of secant. And by earlier in class, we know that this is natural log of secant theta plus tangent theta. Okay. So that's by earlier in class. Okay, I know I skipped a few steps with this one. I hope everything is clear. Please just let me know. Right, we are at the finish line. Finish line. So let's just write down what we need. We need secant theta and tan theta in terms of x. That's what we need in terms of x. Okay. So from our initial substitution, so from x equals 2 secant theta, which is the same as x over 2 is equal to secant theta, we draw the following. So secant theta is hypotenuse over adjacent. So that's going to be x, that's going to be 2, and then this missing leg here, that missing leg is going to be x squared minus 4, and that is by Pythagorean. All right, so recall, we need secant theta and we need tan theta. All right, so tangent of theta is easily readable from this triangle. Excuse me. Tangent of theta is opposite over adjacent, and opposite here is the square root of x squared minus 4, and adjacent is 2. Very good, and from earlier, we don't need well, we can read this off the triangle, but secant of theta was x over 2. So we have everything we need. So final answer. So let me just rewrite the theta. Ln secant theta plus tangent theta. This is equal to natural log. Secant theta is x over 2. And tangent theta is square root x squared minus 4 over 2 plus c.